So my NSF Career Award deals with understanding the thermomechanical response of surface layers from machining and finishing processes and how that processing of the surface during the manufacturing process affects the performance of components made using these processes. So on one end of the spectrum, you have the negative side. So in the aerospace industry, the AIA, which is the Aerospace Industry Association, in a 2019 report, they report that about 25 to 30% of uncontained engine failures, so failure of engine consequent crashes and loss of human life for airplanes, are caused by machining and finishing process induced anomalies. Now, on the other hand, I think industry and a lot of research nowadays looks at this as sort of a preventative paradigm where we can actually proactively engineer surface properties and increase their performance, the sustainability, the ability to repair things more efficiently, the ability to use them longer, do more with less, essentially. My research program is funded by industry. It's been funded by the Department of Energy, Department of Defense. But with this NSF award for 5 years, having this guaranteed funding, being able to support a student, being able to know that I'm going to have travel funding for certain things, it really makes such a big difference. It'll allow my team and I to actually construct new experimental apparatus. It'll allow us to really investigate some key questions that hopefully can solve problems that people have been dealing with for over 100 years now. So we look at the material response of primarily metals, but also composites during finishing and machining processes. And so we use very high-speed microscopy. We tend to look at very small objects at the micron scale, so a millionth of a meter moving at about a meter per second. So we need frame rates on the order of 100,000 to close to 1,000,000 frames per second to actually image some of these events at very high magnification. So we try to understand what is the mechanical response of the material, what's the thermal response of a material. We use modeling techniques, so we use that experimental data to calibrate and validate models of processes. And then finally, we get into some artificial intelligence, AI, where we actually can increase the efficiency of our experiments and increase the accuracy of the models. I like to think about it kind of like Legos. So it's a modular approach, and we take the best from each world and we try to sort of fuse them in a way that's more than the sum of the parts. I think one of the things that I'm personally very excited about is the challenge, and I also think opportunity, both here in Kentucky and really nationally, to address what's commonly known as the skills gap in manufacturing, but what might also be called a recruitment or maybe even a generational gap. So we're actively recruiting women, underrepresented minorities, and really anybody that could be a great asset. And I have a vision for the University of Kentucky really being a key contributor to the aerospace industry in particular, but also the defense and biomedical industries to really provide the talent that can drive the next generation of advancements in industry.